is Joachim Soledal. I'm one of the organizers of this conference. I'm here with Dr. Haiping Huang, who will have a talk of the application of molecular markers to reconstruct fire history at archaeological sites. He's a professor here at the University of Calgary. So please take it away.
Okay, thanks for the introduction, and hello everyone, and thanks for the organizer and invite me for the talk of this kind of related with archaeology. So this afternoon I will talk about the application of molecular marks to reconstruct fire history at archaeology. The co-author for this is Wenran. She will give a talk for the NRK and some saturated hydrocarbons, and Steve and the Julio you know already. So I'll briefly introduce a little bit of my talk and give you a little bit of background of the sample and the method. Main part of my talk is the evidence of the fire in the old Pyrogenic, and a little bit of summary for the talk. So yeah, the fire is a kind of common phenomenon. It's everyone knows this very well, and it's caused by the biomass burning, volcanic eruptions, and the human activity, occasionally in the archaeology site, because the human activity can involve a little bit of fire. So fire itself is a very important tool for the human to manage ecosystems and the land use since prehistoric times. Fire can affect the vegetation distribution, the carbon cycle, and the climate. So it's kind of all relevant, but the link between the climate, vegetations, and the fire regime are quite complicated. There's no obvious kind of one-to-one kind of relationship can be easily established. So the side we are looking for is all see this quite a few times in the previous talks is from the old Pyrogenic. So this is a column in the left kind of side column is a indicator the lithology variations and a few events in between. So the sample we have is a little bit in the lower beds and a little bit between 1A, 1B, 1C, 1D. Those are events of the volcanic ash deposited with tuff. So those are very good for the constraint of the times. We got a very kind of a time constraint from 2 million years, 1.8 million, and the section we covered around 230,000 years. Right hand is a kind of several other columns or the excavation areas. We are focused on one specific spot is 63. With the samples we have. So this is detailed samples we have in these studies. From the very bottom one is called the CFCT. This is the coarse field spar crystal tuff. So from this upwards, we have around 20 samples. So those samples are mainly from the sandstone, a little bit of shell in between. And there's a few kind of sparked here. The colored one is 1A, 1B, 1C is tuff. So the most of those kind of sediments or the samples we have is from the alluvial, fluvial. So those are river related or some floodplains. Occasionally we go to the lake in kind of invasion or transgression. So 3 times of lake transgression, the first lake, second lake, and the third lake. So the lakes bring a little bit of kind of fine grain sediments, and most of the others are a little bit of coarse grains. So here is the pictures you already see before. Some slides or some previous presentations show you the kind of appearance of those outcrops or the excavation sites with the different lithologies and different marks of the tuffs. And most of them are sandstone. Occasionally we have seen some clays, especially some kind of wax clays and some lake carbonates. So a little bit kind of shallow lake deposit with a little bit of fine grain sediments. So we got all those samples in our lab. Then we started the processing. So when we do the samples, we mainly try to understand those molecular compositions. So we need to extract those molecular compositions through the very simple tools called the Soxhlex extraction. So we put the sample in the powder, then we extract with solvent. Once we get the extractors, then we separate into different fractions, saturated hydrocarbons, aromatic hydrocarbons, and the polar fractions. Then we put those fractions in the machines. As the previous talk, we already explained that the GC is a very common or very useful tools to separate those mixtures into different individual components or individual compounds. Then we can get the spectrums to identify what kind of a specific compound we have in these samples. So this is just illustrations for the sample. We can use those for analyze for molecular compositions. We also combine some other kind of tools or the technologies, especially the charcoals. So charcoal itself is believed to be product of the kind of plant remain during the incomplete combustions. So it's good indicator for the paleo fires. So in the left side of the slide is the numbers being quantified in the cubic centimeters of the micro charcoal in particles. You see the different kind of samples have variable of the count or the numbers of the charcoals. So it indicates the charcoals is a kind of residuals of the combustions. In the right hand of the slide is in the kind of enlarged and microscopic. You can see very kind of detailed structure of charcoals, and the bottom side is a molecular kind of composition for those charcoals. Obviously, most of those charcoals are composed by the very condensed aromatic rings. There's a lot of aromatic rings being fused together. So those are very big size of the molecules, or we are not a RAM machine for those charcoal directly. We need to get a small components, especially those small number of rings. So those are called the PAH, those are polycyclic aromatic hydrocarbons. There are two main kind of origins or sources of those aromatic hydrocarbons. One is called the pyrogenic, mainly from the combustions. So the natural kind of biomass combustions, volcanic. In the recent sediments or the kind of very young sediments, we also have some human activities like the fossil fuel combustions get a lot of the printers in aromatic fractions. So another source of the aromatics from the land plant or the algae is deposited in the sediments, then diagenesis, catagenesis transform those molecules into the individual components like the saturated hydrocarbon, aromatic hydrocarbons. So both those routes can generate the aromatic hydrocarbons. So the aromatic hydrocarbons, we analyze them in the number of rings, those 2 rings, 3 rings. So those are different rings that have the different kind of connect with the different sources. Most of those can be derived from both origin, and some specific compounds like anthracenes, benzoanthracenes, and a few others are mainly from the kind of combustion or the pyrogenic origins. So let's move to the specific site. We're looking for the old Pi Gorge. So there's a sample here. So this is we extracted a lot of those samples. We get this is a few we call the spectrum. So those are just a few individual components. We don't need to go very details, but from the appearance or the looking, you can see some difference or some changes are kind of in different samples. So those are about 20 samples in this specific columns. Those are a few different individual components. All those are aromatic hydrocarbons, with a few of them are with oxygen-bearing compounds. So we go more details for those compounds. Here is the concentrations we calculated for those samples. So this left side is the concentration in the EOM, is extractable organic matter. So this is the micrograms of a gram of per gram of the extractable organic matter. This is the ppm. Then the right side is the gram of the dry water of the sample, get a nanogram of the concentrations. Both concentrations show similar patterns. The lower bottom portion have a little bit high concentration. In the middle sections, slightly low concentrations, and concentration being increased again. So we want to understand where those pHs come from. Then we use some commonly used to differentiate the source. We call this diagnostic ratios. So those ratios are different, help us to differentiate the source. So most commonly used is fluorines over the pyrines. So fluorescence is like if this is a little bit more enriched or high bonded than the pyrines, indicate the pyrogenic. If the pyrene is more enriched than the fluorines, then indicate the pyrogenic. So in our samples, only those 3 bottom ones have a little bit kind of indicated pyrogenic, like from the petroleum related or some diagenesis, catagenesis related. Majority samples in our study, the sample split is from the pyrogenic. That means those fluorescence ratio over the pyrene is higher than 1. So this ratio is higher than 0.5. So majority sample indicator. So this is consistent with our sample background because of the sediment itself is mainly from the meandering or some fluvial. So there's not a kind of deep lakes, so it's not well preserved for the organic material. Those are the transported from the outer sources. So this is another commonly used diagnostic ratios, use the benzoanthracene against the chlorosense. So those ratios are also quite used in the recent sediment or environmental samples to indicate the pyrogenic over the pyrogenic. So ratio itself here is not kind of very indicator for the pyrogenic because ratio normally like a bigger or larger than 0.3, we can say this is the pyrogenic, is below 0.3, is mostly pyrogenic, but the pattern of the ratios is similar as the previous ones. So this is probably the benzoanthracene is a little bit less stable in this kind of environment because all those are very oxidized sample kind of environment. Then we go to a little bit more details to understand what kind of combustion or the fires possibly occur in this kind of specific areas. So we use a ratio of the phenanthrene over the mesophenanthrene. So phenanthrene is, we call this like the parent compound without any alkylations. Mesophenanthrene with a meso on. So this is we call this alkylated or mesolated kind of component. In the geological samples, mostly in the very high matured or the pyrogenic kind of original samples, we have more parent component. During the diagenesis, catagenesis, we do have we call this the mesolation or the alkylation. So we got a lot of the alkylated kind of phenanthrenes. So this ratio, the higher the ratios, indicate the higher the temperatures. So we see those changes from the bottom gradually going move up. Those ratios are increased quite dramatically, and we're supposed to explain or interpret these intervals a little bit high temperature combustions, then gradually the temperature going a little bit lower. So we don't know exactly the temperature for this combustion or the fires, probably 500 around. Then this is 300, 400, probably a little bit kind of lower. So then we try to link this kind of indicator to the vegetations. What kind of the plants are supposed to be in this time of the sediments? We have some other evidence. Then I'll explain a little bit more for the temperature kind of explanations for this specific kind of intervals. This is some other indicators. We use this, as I explained, the fluorescence is a kind of pyrogenic kind of origins. This is a phenol alkylated naphthalenes. Also can be both pyrogenic and pyrogenic, but the ratios see clear patterns very similar as the previous indicators. So indicators the compound sources from these sediment sections have different origins. So most of those upper portions are most likely dominated by the pyrogenic, and the lower sections a little bit more possible of the pyrogenic origins. And then we're going to see some other compound. Here is two typical kind of oxygen-bearing compound. We call this is two benzenes with a phenol kind of type function groups. We call the benzophenol. So this one is also show very different from the lower sections or lower part of the samples to the upper parts. They see some different kind of ratios with the phenanthrenes. Another compound is also very commonly used to indicate the oxidation degrees is the 9H fluoronones. So this one is also see the difference in the lower sections, a little bit less oxygen enriched. The upper sections more oxygen enriched. So that indicates the oxygen kind of concentrations increase or the oxidation degrees is more completed in the upper sections. And we have a nice sample set here from the saturated hydrocarbons. I think Wenran will talk this more details in later sections. So this is from all the previous compounds from the aromatic hydrocarbon fractions. Here is the total kind of the saturated hydrocarbon carbon fractions from the GCMS. So this is like a GC chromatogram. We call this the TIC, the total iron chromatograms. So for the samples, we have the different very obviously. The lower sections, you see some of them are a little bit busy here, but they didn't see too much individual component being identified. This sample is a little bit different. We have regularly distribution the normal alkanes, and those numbers are carbon numbers with an alkanes. And this bigger pictures is the internal standard we added to for the quantifications. So all those lower sections, you see the N-alkanes is sporadically occurs, and a lot of the branched alkanes or some cyclic alkanes being more enriched. Then move to the little bit up, so above the 1A and below the 1B. Those sections we see the very different patterns of the saturated hydrocarbons, dominated by the very high molecular odd numbers N-alkanes, 29, 31, 33. So those are all the odd numbers. Even numbers also have, but very lower relative abundance. So this is a very good indicator for the high plant, especially the land plant is very unique, as those dominated by the high molecular normal odd numbered normal alkanes. Then move upwards, you see again, this is quite busy with a lot of the branched alkanes, cyclic alkanes, and the different kind of alkanes. And there's normal alkanes, there's a high molecular normal alkanes still there, but the relative abundance is a little bit lower. So we interpreted these overall sections. So the lower portion, the sections more like a little bit reworked organic material from the previous sediments being carried, being redeposited here. So those are most likely not the diagenetic kind of aromatic or the N-alkane. Those seems like a highly matured source rock being redeposited here. So this is section a little bit called zone 2 is more like the high plant. Those are more bigger trees over here. Then move up the top sections is more like the grassland. So those are a little bit lower plant and a little bit the herb stuff. So make those the combustion temperature a little bit lower than the middle sections. So this is a kind of temporary understanding for the sections we have. So here a little bit of brief summary. The pH recorded the signal contributed by the external source rather than diagenetic. This external is just a, So this is like transported from the combustions of the surrounding areas, not directly kind of the plant being buried from the in situ. We have divided the section into 3 zones from the CFCT, the coastal field spar crystal tuffs to the 1A. This is like zone 1, dominated by the pH, dominated by the pyrogenic. Those are probably the reworked or redeposited sediments. Zone 2 is from 1A to 1B, dominated by the high plant. So the temperature of the combustion is relatively high. Then zone 3 is above the 1B. So those temperatures are a bit lower, we understand, probably dominated by the grass plant. So those are the currently understand, and I think the pH is a very good tool to evaluate the occurrence of the fire. Obviously, the relationship between different proxy or different parameters are not the same. So the sensitivity is variable. So we need to combine with some other kind of indicators like charcoals or some other tools to verify the combustion kind of situation. Unfortunately, we didn't kind of get very solid evidence see the human activities in this specific site because the sample number is limited and understanding for this result is very preliminary. So hopefully we can get more samples and have deep understanding to find any specific kind of signatures from the human activity. So that's all from my talk. I'm happy to take some questions from the audience.
Thank you very much for that talk. That was really interesting. We do have a few questions. So I will start off with this one here. how does fire impact the preservation or destruction of phytoliths and pollen?
For the what? Can you repeat the?
How does fire impact the preservation or destruction of phytoliths and pollen?
Yeah, I don't know. The mostly depends on the kind of fire itself. If the bigger fires, I think most of those small spores, pollens being combustible, they are kind of easily being destroyed. But I don't think the fires being like last for a longer time. Mostly it's a seasonal or occasionally the fires, and the other times the fire is not there. So those are not all those happen at the same time. I think the preservation for those pollens and the spores that can be in the non-fire times, because I think the fire itself can combustion all those stuff. But I don't think the time the fire will continuously happen all year round.
Right, makes sense. We have another one, a little more specific. Can carbon isotopes be extracted from the charcoal to determine C3 versus C4 origins?
Yeah, this I think the previous talk this morning, the Australia, the talks are very nicely kind of explained the difference between C3 and the C4. Myself, I didn't have the sample to do all those isotope analysis. I think it's in principle, theoretically, yes, it's because the C3, C4, the compositions and the photosynthesis kind of process are different. So their isotope fluctuation degrees are different. So the signature preserved in the C3 and the C4, I think theoretically they are different. They can be differentiated for the C3 and C4. Yes.
Okay. We have another one here. Have you had a chance to compare the fire biomarkers with the N-alkanes to see if they correlate? Meaning, do you see more fire evidence during the open plant environment periods?
Yeah, that's the ongoing work. Yes, I think the fire mainly kind of generate a lot of the PAH, the polycyclic aromatics, also the N-alkanes, especially those high molecular N-alkanes, they can be preserved in the fire residuals. I think the concentrations or the distribution of those N-alkanes can be indicated, but it's not directly indicated the fire itself. Can be more specifically indicated the source of those organic materials from the land plant, what kind of plant, or is any in situ kind of like algae or some water plant being preserved as a lower plant, herbs, or the high plant. Different trees probably have different specific N-alkanes. Some is like dominant by 23, some is 27, 29, 31. Even some specific plant have the C33 dominant N-alkanes. Yes, I think the N-alkanes is more useful for the differentiate the species of those plant or the organic input. But the PAH is more indicated the process is being combustion or the fire occurrence.
All right. I think this is also related there, this next question. People often use burning temperature from high versus low molecular weight, PAH, as a proxy for anthropogenic versus natural fires. Is this a good way to approach fire use in human evolution?
Yeah, personally, I didn't have very deep understanding for these questions because I didn't have my go-to proxy to indicate the temperature of the combustion. Well, I read a bit of basic knowledge from the literature. Honestly, I would say I don't know the answer.
That is also sometimes the best answer that you can give. I'm not entirely sure what this question refers to, but you might be able to glean a little bit more from it than I do. This one says, what epochs/periods were these high temperature areas, zone 2 in parentheses?
Yeah, those are because we didn't have the details, the exact proxy to indicate the temperature. Currently, we just have one specific ratios with the phenanthrin of the mesophenanthrin. So ratio increased dramatically, then that means the parent compound compare with the methylated or alkylated compounds, the proportions of those component distributions is very different, indicate their generation temperature is different. So we know that temperature is changed during this process, but we don't know exact temperature itself is say 500, 600, or the 300, 400. We don't know this, but we know the temperature itself is variable from a little bit lower temperature going to the high, then cool a little bit lower or down again. So the cycle of the temperature is clear, but with the number we are short is the exact number of the temperatures. We probably can find more proxies for the temperature itself in the future study.
I see. That's really interesting. This is also slightly related to that. And after this question, we have one last one. So this one reads, what are the main differences between the PAH from petroleum and those from fire processes?
Yeah, the PAH from petroleum is dominantly the difference is a lot of the petroleum-related PAH has a lot of alkylated kind of methyl, dimethyl, trimethyls, a lot of alkylations in the aromatic compound itself. Then a few of those, like the combustion or the pyrogenic originated, like the anthracene, benzoathracene, fluorescence, a few of those are like the dominated in the pyrogenic origins. Majority of them can be from the petroleum originated, but the concentration is relatively low. So the alkylation or the degree of alkylation is a kind of a very good indicator for the petroleum originated or the combustion originated.
Okay. And then the last question here. How has this technology and these methods developed in recent years? Where do you think this research will go in the future?
Yeah, this is again the ongoing stuff because a lot of, I think, mostly probably, yeah, rely on more computer or the AI kind of stuffs because the traditional technology we use the GCMS combined with the microscopic is still can provide the very, very basic database because your bigger data or the large database rely on the basic analysis. So we think probably integration all those basic understanding with the small tools machines and combined with the AI or the bigger large database kind of analysis statistical stuff. So I think those combination will be with the two solutions or the routes going forward.
I see. It's really interesting to think about the applications of AI in particular for these sort of analyses and research in general, I think. But with that, that was the last question. Thank you so much for answering the questions and for your wonderful presentation.
Yes, thank you. Thank you. It's my pleasure.
I hope you will stay around for future sessions as an attendee. And thank you once again.
Okay, thank you. Bye.